Hi guys, welcome to this introduction of the next few units. The units are dealing with the basically stars in general. We just basically completed the sun, and now we're going to take from what we learned from the sun for other stars. So the study of other stars, basically in terms of their structure, their composition and size and all of that, was a subject that was done at least, I mean, it was started a long time ago, but around the turn of the 20th century, at that time, we have had good enough tools to study spectroscopy. So here is the deal. Before we do that, we needed to have some sort of an understanding of the size of those stars, their basically masses and also their physical size, meaning their radii, how big they are. So for that, if the star is nearby, there is a technique that we can use, and that is the parallax. So what the parallax is basically is that if you look at an object, even in your room, by closing one eye, for example, and focusing on that object where it is, and then you shift to the other eye and look at the same object, you will notice that that object you're looking at shifts position depending on which eye is open, from one side to the other versus the background, versus whatever is behind it, okay? The faraway objects. So that is really what the parallax is. So now we use that technique for the nearby stars, not too far away from here, basically where the sun, where the Earth changes position with respect to the sun. 6 months from today, sometime in October, 6 plus, well, right now May, so probably what, November, we will be in a different position with respect to the sun. The sun is, let's say, for example, this is the sun. 6 months from today, we will be on the other side. So this whole distance, which is 2 times the astronomical unit, about 300 million kilometers, namely one astronomical unit is 150 million. So twice that is about 350 million. So as if we close one eye and open with the other, basically, we have telescopes geared toward those stars. I mean, looking at those stars. So now the shift, even with visual, at least for the nearby one, the shift in position of that star versus the background stars is what we call the parallax. If we measure that shift, namely the angular displacement of that star versus the background, and use simple geometry and the fact that we know the distance from the Earth to the sun, that will help us find the distance to that star. So that is one thing. So that gives us at least the distance. In terms of sizes, we use different techniques. At least this is for the nearby stars, I was saying. Other techniques need to be involved for all the faraway stars. And the faraway stars, or even for the nearby stars, there is another technique which has to do with how bright the star is. Remember the inverse square law? Light, as it leaves the source, starts to drop like 1 over distance squared. If I know how much luminous that star is, how much luminous that star is, basically how much radiation is emitted from that star, then, and I can measure its brightness, basically how dim or bright it appears right now from us, then I can use the inverse square law to find the distance. That is one thing. The other thing also is that we can find the maximum frequency, which we can measure, maximum wavelength, which we can measure for a star, using Wien's law, namely that maximum wavelength can tell us the temperature of that star. Using Stefan-Boltzmann law, we can actually find how much the star is emitting per unit area. Okay, and again, we have now all kinds of different techniques that we can utilize to find the sizes and basically the distances to those stars. One of the issues that later on basically emerged is that because now spectroscopy became a strong field, basically, that is the study of the spectrum that is being emitted, or it's coming from the background and is absorbed in that case by given object. So here is the deal. When we looked at the stars, we saw that they're missing some lines in their spectrum. So the theory is the following. A star on its surface has a surface temperature. For the sun, it's 5,800 Kelvin. That temperature radiates energy, and that energy, those photons will go through the atmosphere of the star. Now, depending on what's present in the atmosphere of the star, all the gases, mainly hydrogen and helium, plus traces of other lighter elements like lithium, beryllium, and even heavier elements. Now, as the light is going through that atmosphere is being absorbed by those materials. The frequencies that correspond to the oscillation, to the excitations of those elements will be missing from the spectrum. This is called the absorption spectrum. So if we study the absorption spectrum of different stars, we will find that they present strong absence of certain elements spectra, meaning that they are present in high quantity on that star. So based on that, we classified the stars based on these properties. And the classification came to be known as basically O, depending on how much concentration of hydrogen and helium and the other elements, or lack thereof, to, and then B comes the B. So these letters are the logic for them. I lost it and I don't know what it is, honestly. But the point being in here, you have an O, B comes next, A comes next, F, G. The sun turned out to be a G star, G, and then K and M. So those are the original classifications. I mean, mnemonic to remember this one is that I memorized, and it's actually textbook mnemonic, is that O, B, A, fine, girl or guy, kiss me. So that's basically one way to remember it. And the G in this case is the sun. It turns out that those spectral lines, they are immediately related to the surface temperature of the stars. And that is because of Wien's law. Remember, Wien's law says that the temperature is inversely proportional to lambda max. Lambda max is the maximum wavelength at which that star is emitting, with a constant in the numerator. But the constant is irrelevant at this point. The point being in here is that these two properties, namely the temperature and the wavelength, are related to one another. So stars that are extremely hot on their surface will basically ionize the hydrogen in their atmosphere, and we even ionize the helium in this case that's present in their atmosphere, and the spectral lines will be properties of those ionized materials. Stars that are less hot, they will not be able to ionize at least helium, and they will have different spectral lines. So those properties, those basically spectral lines, are immediately correlated to the temperature of the surface temperature of the stars. Hence, all stars are super hot stars. Their surface temperature is over 30,000 Kelvin. Then the B stars are less hot, and so on and so forth. So that's really how the classification is. G, which ranges from 5,000 to 6,000 Kelvin, is where the sun is. 5,800 is closer to 6,000, but it's still in that range. So the sun is a G star. As a matter of fact, the sun is a G2 star because there is a finer classification, actually, that goes from the hottest to the least hot, and that uses the numbers G1, G2, and so on. So same thing with O1, O2, if the case they apply. So that's basically how the classifications are related to the surface temperature. The other point in here in this unit has to do with the introduction of the HR diagram, Hertzsprung-Russell diagram. So what that diagram is, you take all the stars that you have in a certain cluster of stars, or even in our neighborhood in here, and you classify them based on their surface temperature, namely the classification O, B, and so on and so forth, A, F, and G, and K, and M. And there is actually two more classifications, because the M stops around 3,500 Kelvin. So there are two new classifications that drop down all the way to 700 Kelvin. okay? At 700 Kelvin, the star is really too, how should I say, those are the brown dwarfs, okay? You cannot even see them at that temperature because they are really not that bright at all. So the point being in here is that you classify them based on those properties on the x-axis. On the y-axis, you classify them based on their proper luminance, based on how much light they emit, how much energy they emit per unit time. Now, those are the two properties, but then that luminance or brightness depends really on the size of the star. The bigger they are, the brighter they are. Even though you have two light bulbs, both of them are operating a 60 watt light bulb, for example. One of them, if it is too big compared to the other one, produce more light, will brighten the area more if it is big, provided both of them have the same wattage. That's the same idea with the stars. Size matters in here. So the classification, if you look at the graph in the book, you will see that most of the stars, they line up on a diagonal that goes from the brightest or the most luminous, I should say, and the hottest, all the way to the dimmest or the least luminous to the coolest. And it's a diagonal offside, okay? That is called the main sequence stars. The sun happened to be on the main sequence star. Alpha Centauri, binary, I mean, the two Alpha Centauris, A and B, they are actually on the same side too. One of them is slightly bigger than the sun, the other one is slightly less than the sun. And then you have the dimmer star, like Proxima Centauri, which is the closest star to us, also is actually on the M side. It's a lot cooler than the sun, around 3,500 Kelvin, and also a lot less small in size, which means that its brightness is very, very dim. So that is one thing. And then you have the bigger stars, of course, on the other side of the spectrum, like Ceres, which is actually a binary also. You have Ceres A and B. The A is the one that is the main sequence star. So that is basically, and then it extends all the way up there for big stars and much hotter stars. And then you have stars that are off this line, of that diagonal, on one side that are giant, because the HR diagram also gives you some sort of understanding of the sizes if you look off diagonal too when you start cutting those lines. And you will see that stars that are the size of the sun, stars that are bigger than the sun, and stars that are smaller than the sun. So the stars that are massive, and it's still they have less less temperature on their surface, but because of their super size, in this case, they're actually very, very bright. Case in point, Betelgeuse, for example. So they're actually lining up on the other side. They're constituting the giant and the supergiant, basically red stars, and even blue stars on the other side, closer to the hotter ones. Now, this is on one side. And also, on the lower side, you have the so-called white dwarfs. Those are stars that are at the end of their life, and basically they consumed all of their hydrogen in their core, and now they migrated below, in a sense that at that point they are less bright than before, but they're still hot because of that residual heat from contraction and also from whatever is left from the original, basically, star. So those are the white dwarfs. So this is in a nutshell what the introduction of the HR diagram. We're going to go more in detail about it when we try to understand the evolution of the life cycle of stars. Thank you.